he may have ended up here from being mislabeled. Maybe he was supposed to be a green ball, or maybe he's just highly unusual. And generally, we don't want our models to basically cover this blue ball here. This is called overfitting, and it's bad because in most likely case, or most likely scenario, the green balls are going to be right here. So what happens when a green ball is here, like an unseen green ball in the future, but we feed this green ball his XY coordinate that is right here into this model. This overfitting model is going to label it as blue, unfortunately, when in reality, if you see it here with this nice clean model B boundary, it is supposed to be green, the green class. So that's an example of a model that is overfit, probably too complicated for its own good, as opposed to model B, which generalizes well. Model C, on the other hand, is way too general, and it's not going to be a good model. So, as I explained before, this model overfits, this model is ideal or balanced, and this is what is called underfitting. He doesn't fit the data too well. He just gives you a generic little boundary and tells you, yeah, I tried my best, but it's underfitting. So let's go into overfitting. Overfitting is what leads to poor models, and is one of the most common problems faced in AI, machine learning, neural nets. It's a problem I face continuously when training my convolutional neural nets. It always happens, it always tends to overfit on the training data, and we will experience that later on in this course. But what it means basically is overfitting is when our model fits near perfectly to our training data, as in he has very high accuracy on the data he was trained on, maybe even high 90s or 99.9 something. However, on the test data set, which is the unseen data, he is going to be performed poorly because he's now basically modeled after the training data but can't generalize well the data he hasn't seen. So that's what happens when you try to pass a new point to this position here. Exactly what I mentioned before. Its true color is supposed to be green, but it will be classified as blue. Models don't necessarily need to be complex to be good. They need to generalize well. So, how do you know if you're overfit? Well, that's why I mentioned test data previously in the beginning of this slide. We need to test our model on test data. And in all machine learning algorithms and stuff, we always use a test data set. And basically, if we have entire data sets, say for 1,000 images, we take 700 and we train on those 700 labeled images, and we reserve 300 as test data. That 300 is critical because it tells us how well our algorithm or model performs on data the model has never seen before. This is a very common case sometimes with overfitting. 95% plus accuracy, but on test data you get like 70%. It's a perfect example of overfitting. So overfitting illustrated graphically. Here's what happens. Remember I mentioned epochs? Now later on in this chapter, I discuss exactly what epochs are. It's basically every time we send the full training data set into our training algorithm, we have completed one epoch, and we need to train for maybe hundreds of epochs sometimes to get a good model. Usually that's not the case. Usually you can get away with training 20 to 100 epochs, but generally that's what we have to do to get the best models. So this is an illustration of what overfitting looks like. So look at the training loss here in red and accuracy. Loss is going down quite well. Accuracy is going up close to 100%. The scale of the accuracy is on this side and loss is on this side, and epochs are to X. And now look at the test. The test loss basically just fluctuates between 1 and 1.5 and actually goes up in the end. It's not good at all. And look at our test accuracy. He's hovering at abysmal rates of like below 50%. And while his training data is at 100%, this is actually extreme overfitting, to be fair. It doesn't actually ever get this bad. At least I've never gotten it to be this bad. But it's a good example of what we actually see happening in the real world. Good training accuracy, poor test accuracy. And that's overfitting. So how do we avoid overfitting? Now there are many techniques to avoid it, and I'll discuss it soon in this slide, in this section. Now, overfitting is a consequence of our weights. Our weights have been tuned to fit our training data, but don't fit. They're overtuned in a way so that they don't perform well on test data. And we know our weights are a decent model, just too sensitive to the training data. So is there a way to fix this? What I mean by too sensitive, I mean it's just optimized exclusively for our training data. So we can avoid overfitting by using a smaller, less deep model. Deeper models can sometimes find features or interpret noise to be important. Noise was an example of this here. This clearly wasn't that important, but yet a deep model will actually try to figure out and model this. So that's because due to their deeper abilities, deeper networks have abilities to memorize more complicated features. And that's called the memorization capacity. But there's another way, and that's called regularization. I don't often recommend, or I shouldn't recommend, using less deep models to get better results, because there are other ways around it, and you want to actually always have a deep enough model to represent complicated patterns in your data. So let's see what techniques we can use to regularize. So what is regularization? It's a method of making our model more general to our data set. So basically, regularization will take a model that produced a decision boundary like this and sort of tweak it so that it becomes like this. And let's see. Now, it's not actually doing it. That's the actual term of regularization. We basically want to get a model like this and not like this. And let's find out how we do that. So there are a few types of regularization. There are actually more than this, but these are the basic types. There's L1, L2 regularization, cross-validation, early stopping, dropout, and data augmentation. So let's look at L1, L2 regularization. These are techniques that we use to penalize large weights. Large weights of gradients manifest themselves as abrupt changes in our model's decision boundary. And by penalizing them, we're effectively making them smaller. L2 is known as ridge regression, L1 is lasso regression. Now, there's a lot more theory behind these things here. I'm just basically showing you the formulas of what they actually are. So, as you can see, this is basically what ridge regression, or L2, is here. This is our MSC here, but we're actually doing something with the weights here. What are we doing? We're applying a constant here over 2, and the sum of the weights squared. And L1 is not squared, it's just the absolute value of the sum of the weights. So this parameter here controls the penalty we apply. So via backpropagation, the penalty on the weights is applied to the weight updates. So the difference is that between them basically is that L1 brings the weights of unimportant features to 0, thus acting as a feature selection algorithm. You may not know what feature selection is, but if you want to know what feature selection is, it's basically trying to find out, we have like 20 inputs, what input is the most important to our output. Okay, that's also known as sparse models as well. Whereas L2 penalizes it even more. It doesn't bring it down to 0 though, okay? So effectively what we're doing here, just remember, L1, L2 prevents our weights from being too large so that we don't have abrupt changes in our model. Abrupt changes basically mean things like, go back to here. We basically try to make this smoother instead of having this abrupt gradient changes here. So let's go into cross-validation. Now, cross-validation is something I rarely ever use because I'm just not that used to using it. I used to use it a lot doing previous machine learning stuff, but in deep learning I don't use it often. But if you want to know what it is, it's quite simple actually. Basically, cross-validation, or also known as k-fold cross-validation, is a way we split our data set, our training data set, into different folds, and we train on those folds, and we basically test on the other folds afterward. So let's look at this here. This here is our test fold here, our validation set, and our training set. So what happens is that we train on these 4 folds here, and we test on this. Then we train on these 4 folds here, we test on this. What this does is that we don't actually have any unseen data in this model. What we're doing is just we're continuously testing on segments of the data and then training on segments of the data and then testing on a different segment. It reduces the overfitting, yes, but it also slows down the training process. Now, early stopping is something we can actually automatically do in Keras. Basically, we can set something in Keras that tells us if our loss stops decreasing, stop training. So if we set our model for 100 epochs, but say at epoch number 30 something, the loss stopped decreasing, it's going to stop training somewhere around here when it realizes that. And it's going to give you this model here, the one with the best loss. The reason we do early stopping is that sometimes if we keep continuously training over and over number of epochs on our training data, it tends to basically overfit on that training data. So we need to actually stop it early sometimes so that overfitting does not occur. And let's talk about dropout. Dropout is actually very easy to implement and extremely useful. So dropout refers to dropping nodes, both hidden and visible, in a neural network with the aim of reducing overfitting. What do I mean by dropping nodes? What this means is that in the training process, certain parts of the network are ignored during the forward and back propagations. This is a way of actually making our network have some redundancy in a way, but what it also does is that it actually adds regularization to our networks. It helps reduce the interdependency between learning, or neurons while learning. So it actually leads to more robust and meaningful features. So in dropout, there's one parameter we use, it's called P, and P is the probability that the nodes are kept or dropped out in the training process. So the only consequence of using dropout though is that it almost doubles the training time to converge during training. So this is a good illustration of dropout. This is how a standard neural net works when we train it. And after applying dropout, let's say this is a fairly high value, these nodes here are ignored, and these nodes here are used in training. And lastly, well, it's not the last method of regularization, but it's the last one I will teach in this course because the others are actually quite exotic and not commonly used. So this one is called data augmentation. Remember I said you need lots of data to train a network? What if you don't have? Well, in computer vision especially, it lends itself naturally to data augmentation. What we do is we take our input data set, we have one picture of a dog, but how about we just make some manipulations to this image? We can rotate it completely. We can, I think this one is just mirrored back here, and this one is actually zoomed in a bit as well. So that is a way we can actually expand our data set. So in this section 6.9, I discussed some terms I've used before, terms such as epochs, iterations, and batch sizes. I'll discuss it a bit because a lot of times in tutorials and in lectures you'll hear these terms being used, and sometimes they'll be mixed up, and I'll tell you why afterward. So epochs. Now I'm sure you've heard me mention it quite a few times before. So what exactly is an epoch? An epoch occurs when the full set of training data is passed or propagated and then back propagated through a neural network. So the process of one epoch means that we've trained our neural network on our full data set and updated all the weights. So after the first epoch generally, we will have a decent set of weights. However, it's never enough. You need to train for several epochs over and over and over to continuously updating the weights so that we converge. And by converge, I mean get the lowest weights, get the lowest loss possible with those set of weights. Now batches. Now, in every time you train in Keras or any CNN or any neural net, you'll see they specify how much batches do you want. Now, batches aren't super critical like batch size. It doesn't generally affect your results that much. But what you need to do though, the bigger the batch, generally the better. However, you're limited by your RAM or video RAM if you're using GPUs. You can't put all the data at once into a batch, so you need to split it up. So generally if you're using image data and it's basically resized to something like say 100 by 100 pixels, you can use a batch size of maybe 16 to 32, depending on how much RAM you have. I'm assuming you may be using at least 4 to 8 gigs of RAM. So a batch size of 16 is generally quite good. So actually, I failed to mention one thing though. If your batch size is 1, you're effectively just doing stochastic gradient descent, which is not a very effective way of doing gradient descent. Mini batch gradient, I believe that's the name of it. But using mini batches is basically the best process to actually train and implement gradient descent. So what about iterations? I used to get confused between iterations and epochs quite a bit. However, the difference is quite simple. Iterations are just simply how many batches we need to complete one epoch. Now, the reason I used to get confused for was because I had a professor who would say you train your neural net for 10 or 100 iterations. And that was because I think he was using MATLAB to train. And in MATLAB, at least maybe in the library he was using, iterations were actually meant as epochs. And I don't even know what epochs actually were at that point. They were just iterations. But I mean, I don't even know what iterations were called. Maybe they were called batches or mini batches, perhaps. So in our previous example, which on this page I didn't actually discuss, but let's say we had 1,000 samples of data and we specified a batch size of 100. That means you'd be taking 100 samples of that data in each pass in the network to update our weights. So we have 10 basically iterations to complete one batch, as I said right here. So that's it. So now let's move on to how we actually measure performance and understanding the confusion matrix. So welcome to chapter 6.10 or chapter 6.10, where I basically explain how we assess and measure performance of our trained model. As you will learn, there's a lot more than accuracy to determine the model's performance. So we've seen this graph before. This is basically the graph illustrating overfitting, and it was a pretty bad model here. It overfitted quite a bit, but it was very good in the training data. But that's not what we want at all. So let's talk about loss and accuracy. It's important to realize while loss and accuracy represent different things, they're highly correlated, so they're essentially measuring the same thing, the performance of our neural net on our training data. Now, accuracy basically is just a simple measure of how many correct classifications we got over the total number of classifications overall. So let's say we were predicting whether something was a cat or dog, and let's say we got it right 99 times out of 100. That would be a 99% accuracy. Now, loss values tend to go up, not tend to, they will go up when the classifications are incorrect. That is different to the expected target values. So basically, as I said before, they are correlated. So is accuracy the only way to assess a model? No. There are actually other ways, and I'll discuss it too here. So accuracy is important, yes, but it doesn't tell us the full story. So let's look at this example here. Let's say we're using a neural net to predict whether a person had a life-threatening disease based on a blood test. Now, you would think they are yes or no are the basically possible answers. However, those are the answers yes, but those are not the actual scenarios that happen in real life. In real life, or in reality I should say, these are the 4 scenarios that can happen. It can be a true positive, which means that the test predicts positive for the disease, and the person has the disease, so that's good. It can be a true negative, which is the opposite. Test predicts negative, and the person doesn't have the disease, good. However, it can be a false positive. Test predicts yes for a disease, but it didn't actually have the disease. So it's not good, but not as bad as this one, where it predicts negative for the disease, but the person actually had the disease. So let's take a look and see how we use these 4 scenarios to assess the accuracy of a model. So I'm not sure if you've ever heard of these terms, but there's recall, precision, and F-score. Now, recall is defined as this: number of true positives over the number of true positives plus the false negatives. If you remember correctly, false negative is this here, and true positive is this here. So what recall is telling us is that how many true positives did we get? So how many times did we accurately predict that a person has the disease over how many times the person actually had the disease? So that's what the denominator in this is. How many cases of the diseases were there, and how many times did we get it right? That is effectively what recall is. Now, precision of all our samples here, how much did the classifier get right? That's what precision measures here. So we have, again, true positives here over true positives plus false positives. So let's go back, to false positives here. False positive here is basically the test predicted positive, but the person didn't have the disease. So that's the denominator here. So how many times did how many of all these samples, how much did the classifier get right? And F-score is an attempt to actually measure both recall and precision in one. Okay, so let's take a look at an actual example here. So let's say we've built a classifier to identify gender, male versus female, in an image, where in this image there were 10 male faces and 5 female faces. So we run our classifier on this image and it picks up 6 male faces. Now, out of those 6 male faces, 4 were actually male and 2 were female. So how do we work out our precision? Now go back to the formula. Our precision is number of true positives, which was 4 in this case, because we got 4 male faces right out of the 6. And how many same true positives plus false positives? So how many false positives were there? There were actually 2 false positives, because it picked up 2 females here, but told us they were males. So those were false positives. So that's 4 over 6, so 66%, 0.66. So let's work out our recall now. Our recall is the same, true positives over true positives plus false negatives. Now, what's the false negatives here? The false negatives here were the fact that 6 male faces. Remember, a false negative in our other example was how much test for disease did it miss. Okay, so in this case, there were 6 male faces that were missed. So it's true positives over true positives plus false negatives, which is 0.4, 40%. So now applying our F1 formula, this here, 2 times recall times precision over the recall plus the precision, that gives us this, and that gives us this final value, which is close to 0.5, which is 0.498. So that's a good example of how recall and F1 and precision are used to actually assess model accuracy. Now, this isn't actually used that often in CNNs, but I actually do use it quite a bit in some models. I shouldn't say it's not that much used. I don't see it used that often in a lot of other researchers. Not entirely sure why, but to me it depends on the application. So if you're predicting something very important, you need to use this to understand your performance. How well is our model actually picking up stuff, and what kind of mistakes is it making? Okay, so it all depends on the domain. So this is a good example here from Wikipedia. It actually illustrates the true negatives, false positives, true positives, false negatives in a little Venn set diagram here, selected elements. So you can actually see the formulas applied here visually. So you can take a look, pause the slide and take a look and try to understand it conceptually as well. So hopefully this helps. The point of this chapter was to actually show you that accuracy and loss are not the sole metrics we use to assess performance. So now let's go on to a review of everything we've just learned. So you've spent over an hour basically going through neural nets in some detail. So I think it's about time we actually do a review and basically try to reiterate everything we've just learned. So let's move on. So let's go over training again. So just to reiterate the steps, we initialize some random values for our weights and biases. We input a single sample or a batch, perhaps, of samples of data. We then compare our outputs with the actual target values. We use those loss values. We use those values now to calculate our loss values based on a loss function here. We then use backpropagation to basically perform mini batch gradient descent to update our weights. Now, it doesn't have to be mini batch gradient descent. It can be stochastic gradient descent or naive gradient descent, but mini batch is perhaps the best. And then we keep doing this for each batch of data in our data set. And each time we process a batch, it's called an iteration, until we complete one epoch or an epoch, which means that all our training data was fed into our model, and we use backpropagation to update the weights. And then we just keep completing we keep performing more and more epochs and stop training when accuracy or on our test data set stops decreasing. So again, this is the training process visualized. I think we went through this before, but just again, let's do it quickly. Input data comes in, or a batch of input data. We get the predictions, compare them to the true targets. We use a loss function to assess how different they are. Then we get an optimizer, and we use backpropagation or stochastic gradient, which basically performs stochastic gradient descent of any other form to update the weights. And then we keep doing this again and again for more and more epochs. Okay, so these are some general best practices I find that are quite useful to use when training neural nets. Definitely use ReLU or leaky ReLU. I'll explain what leaky ReLU is in later slides. Loss functions are definitely, you should always use MSE or some variation like mean absolute error. When you're doing regularization, I always recommend you try to use at least L2. Definitely use dropout, and it's not stated here because this is for neural nets, but generally always use data augmentation if you're training CNNs. Learning rates should be low. 0.001 is a good value to use. We talk more about learning rates in later slides, so for now, just remember 0.001 is a good learning rate to start off with. Number of hidden layers depends on the performance of your machine, honestly. I mean, I would go as deep as you can go, however, that can exacerbate and lengthen your training time so much. So don't try to be too adventurous. Keep a model that you can train fairly quickly on your machine, and that will allow you to experiment a lot, as opposed to training a model for days and then realizing something is set badly and you're not getting performance you want to. And the number of epochs, you should always try to train for at least 10 to 100 epochs. After generally 20 epochs, you can kind of get an idea of how your model is performing. So once you can start off training maybe 20 epochs to 30 epochs at first and adjust your parameters to suit. And then your final model, you want to actually make the best, train it for at least 50 epochs. Okay, so that brings us to the end of our neural network section. Now, a lot of other courses and textbooks and blogs will talk about different types of neural nets and all sort of exotic stuff, but to be honest, you need to understand the core, which is what I just showed you. The core being gradient descent, backpropagation, how training is done, and how to assess your performance effectively, how to avoid overfitting, understand when you overfit as well. So you now have a very good core understanding of neural nets. And now we can begin moving on to chapter 7, which is on convolutional neural nets. The real deal about this course is actually on convolutional neural nets, which is what we'll be training many in Keras going forward. Okay, so welcome to the big famous chapter in this course on convolutional neural nets. This is basically the core of the course, so please pay attention to this chapter. You're going to get a very good explanation on convolutional neural nets, I guarantee it. So what does this chapter include? Let's see. Firstly, I do a brief introduction to convolutional neural nets, or CNNs for short, because that'll save me a lot of time to say that word. So we talk about convolutions and image features in the next chapter. Then depth, stride, and padding. You'll understand that soon. What ReLU is, which we talked about ReLU before, but how it applies to CNNs now. What the pooling is. What a fully connected layer is. And how we train CNNs. And lastly, how to design your own CNNs. So, I hope you're looking forward to this chapter. It's going to be fun, and you're going to learn quite a bit. I guarantee it. Hi, and welcome to chapter 7.1, where I introduce the concept of convolutional neural nets, basically CNNs, as I'll be referring to them throughout this course. So, why are CNNs needed? We spent a while discussing neural nets previously, and you may be wondering, why would we have spent so much time on neural nets if we're now just going to suddenly discard them and go into CNNs? Well, understanding neural nets is critical in understanding CNNs, as they basically form the same foundation for all deep learning types of networks. All of them basically require you to understand stochastic gradient descent, backpropagation, the training process, batches, iterations, all of those things. Basically, CNNs are just a different form of neural nets, and you'll find out why and how and why. So why CNNs? Mainly because neural networks don't scale well to image data. Remember in our intro slides, we discussed how images are stored, which was basically this. You have a grid. Let's say this is a 10 by 10 grid here. So we have 100 inputs here, technically, and each input has 3 different colors. So that's a lot of data. And the grayscale version of this as well. Okay, and RGB would just be this. So, as I said, neural nets don't scale well to image data. And why is that? Let's consider an image, color image, a small color image, 64 by 64 pixels. So, how many inputs is that? 64 by 64 times 3. That's 12,000 inputs already for what is a tiny image here. So therefore, input layer will have at least 12,000 weights, and that is large. And basically, if we even go higher, we'll have 90,000 weights in the input layer alone. And that's not even considering how many more parameters we'll have in the hidden layers as well. So we need to find, basically, a CNN doesn't actually reduce the weights in the beginning on the input. What it does, though, it finds a representation internally in the hidden layers to basically take advantage of how images are formed, so that we can actually make a neural net much more effective on image data. Let's see how this is done. So, introducing CNNs here. This is effectively what it is here. I'm going to go through each of these in detail in the later slides, but for now, conceptually, this is what it is. Remember in neural nets you had an input layer and hidden layers? Well, these are the hidden layers in a convolutional neural net. What happens first is that we have what is called a convolution, where ReLU activation unit is applied to the convolution here. And this convolution here, it slides across the image here, producing values here. Don't worry if you don't understand this just yet. I'm going to go into detail into each one later on. So just feel free to just basically look at this, get familiar with the terms and the diagram, how it looks, but you don't actually have to know what these are yet. So this is what convolutional neural nets look like. So why 3D layers? I didn't mention 3D layers here before, but you can see here that there are depths of layers. Stacks going this way and this way, whereas neural nets were represented in more of a flat diagram here. So 3D layers allow us to use convolutions to learn image features. And by learning image features, you'll get to understand what image features are very soon. And therefore, this allows us to use far less weights in our deep network, allowing for significantly faster training and a lot less parameters to learn. So this is an arrangement of how neural nets use 3D volume. When I said 3D volume, I'm referring to the input being in 3 dimensions here, because we have height, width, and now depth, color depth here. This is for a color image here. So our input, go back to it here, is effectively a 3-dimensional input that is fed into here, and these are all in different dimensions as well. So, just to effectively go, these are the core layers of a CNN. We have the input layer, our convolutional layer, or ReLU layer, pooling, and our fully connected layer here. That's it. Basically, they can get more complex later on, but these are the core layers of a CNN. So, why is it called CNN? Well, it's all in the name. The convolutional layer here, that's this one here, and also in this one here, comes in sequences as well. You can have, this is how we add depth to a CNN, by having multiple stacked convolutional layers. Now, convolution is what allows it to actually learn image features. And I will explain to you again what image features are, but they're basically what our classifier uses to sort of detect what's in an image. But what exactly is a convolution? Well, let's find out in chapter 7.2. Okay, so in 7.2 we are going to learn what convolutions are and what image features are. So let's begin. So before we dive into convolutions, let's take a look at what image features actually are. So when I say image features, I'm talking about interesting things in an image. It's a kind of a vague term, but it basically encapsulates things like edges, colors, patterns, and shapes. This is a dog here that has been, the edges have been extracted using canny edge detector. So image features are basically just that, just basically one narrow thing that we find interesting in an image. By narrow, I mean like a type of category, like edges or colors. This could have easily been a brown color filter, or blue, or whatever, or pattern, color, or shape. So before CNNs came into the picture, scientists did feature engineering manually. Did you see how I just mentioned that these are edges or color extractors or patterns or shapes? Now, what we had data scientists, and I actually had to do this at one time, was extract different features such as histogram of gradients, color histograms, binarization, which means like the threshold image, many different things. And it was tedious to actually do this feature engineering, because a lot of times you're just kind of like messing around, trying different things, and you don't even know what works. And in the end, because you don't have a good complicated model that does nonlinear representations well, you still end up getting basically not that great of accuracy. So these are examples of filters learned by this guy here in this publication. This is basically an edge detector here, multiple edge detectors with white and black, like a zebra stripes all over here, different color patterns together. Now, what are these image features here exactly? Like, I'm talking about image features, but what does it have to do with convolutions now? So what are convolutions? Now, a convolution, before I even tell you how it relates to features, convolution is effectively a mathematical term that describes the process of combining two functions to produce a third function. Now, that sounds kind of vague until I tell you the third function is a feature map. And a feature map is effectively these things here. So now we imagine we're applying a convolution to an image. So that's applying the process of two functions. So we apply the convolutional to an image to get the feature map. So convolution is the action of using a filter or kernel. We use both interchangeably in this course and in research and theory. So it's applied to the input, and in our case, the input being our input image. And the convolutions, this is basically the convolutional process now. Let me just go back to this slide here. So I just want to reiterate that in our case, the input, which is the first convolution here, the input is applied to a function called the filter or kernel, and that produces a feature map. So the convolutional process is basically executed by sliding the filter, that's a filter or kernel function, over the input image. And this sliding process is basically a simple multiplication, matrix multiplication, or dot product over to produce a third function. So how is it done? So imagine this is basically an input image. This is a 2D, it's not 3D in reality, but this is for explanation purposes. And this is our convolution filter here, just some values in a smaller matrix. And this is our output feature map. So what's going to happen in the convolution process? Well, we're going to basically slide this image here over, let's go back to here, over this area here, and then again and again, and you'll see it slowly. So when I mean convolve it, convolving means we basically multiply them here. So as you can see, the values were 1, 0, 1, 1, 0, 0, 0, 1, 1, and these values here were 0, 1, 0, 1, 0, blah, blah, blah. I actually didn't use these values, mainly for simplicity purposes, so I changed them to these values here to make this calculation far easier for us. So by multiplying these two together, we get 0 by 1, 1 by 0, 0 by 1, you'll see it here, 1 by 0, 0 by 1, 1 by 0, and so on and so on, and we just add it up and we get 2, and that forms our first output feature in this box here. So how many times can this 3 by 3 matrix be slidden, is that even a word, can be slided over this input image here? So imagine, let's look at it here, we have one box here, then we can shift it again here, 2, just like this here, and then 3 again. So by sliding it over this box, we fill out now a second value in our feature matrix. And I don't have a third one, but imagine it does a third one here, and then starts again at the second row here. So we have 1 here, 2 here, 3 here, and then again 4, 5, 6. All right, so we have basically enough values. So we have for each row 1, 2, 3, and then 3 times it can be slid across here. So we have 9 values in all. So we can actually fill out this entire thing by sliding it across 9 times. That's how we build our features. So by using what I would call a 3x3 filter, convolution or kernel, we produce a feature map 3x3 where it produces the filter here. Now, you understand this process. Basically, it's simple math. But what exactly are the effects of doing this? And why is this important? So firstly, depending on the values of the kernel, that was the kernel being this blue box here, the convolution, we produce different feature maps, obviously, because we can have different kernels with different values, and they'll all produce different feature maps. So applying our kernel produces scalar outputs, as we just saw. Convolving with different kernels produces interesting feature maps that can be used to detect different features. This is what makes it important. So imagine we have several filters here, each with different sets of values here. And we're sliding it over here, we're producing different feature maps. So what this means now is that we've now processed the input image into basically features that have been extracted. So let's keep going. So it's important to know the convolution keeps a spatial relationship between pixels by learning image features over the small segments that we pass over. This means that the convolution, even though it's reduced in size here, it still sort of retains some of the spatial information in this larger image. Just now, it's in a more compressed type form. So these are examples of kernels here. Basically, an identity kernel does nothing. We have edge detection kernels. So simply having these values in this kernel changes an input image into this. It's quite remarkable. But you can actually write some code or try it on OpenCV and see for yourself. You can specify kernels, define your own kernels in OpenCV, and run some convolutions and produce blurs, Gaussian blurs, sharpened images, edge detection. It's actually pretty cool. So let's take a look at an example of a feature applied, or convolution or kernel applied to an image that extracts the features here. So this is an example GIF that I've taken from NYU. You can actually see how when they apply this and slide it across the image here, what the actual convolutional filter output looks like. So this is the edge detector here, and the other edge detector. It's actually pretty cool. Let's look at it again. There. And the other filter. There. Awesome. So now, as you know, that was just one filter. We actually need many filters in our CNNs. Well, at least as within reason. You don't want to do too much, although there's nothing actually wrong with doing too much. Just increases your training time and model complexity. And it may be redundant depending on your image dataset. So let's assume we're using 12 filters. How do we actually visualize how that CNN actually looks? So this is it here. So imagine we have an input image that is size 28 by 28 and three dimensions, red, green, and blue. So that's why it has some depth here. And this is our convolutional filter, which is basically this size here, 1 by 1 by 1. That's actually the output, of the convolutional filter for each grid. This is our convolutional filter box here, all right? So we're actually doing a one-to-one mapping of a convolutional filter. So it's 28, also 28 by 28 by 1. But now we're using 12 filters here. So each yellow block here represents a single convolutional filter, and there are now 12 blocks stacked here. So what happens is that for each filter, we slide it across, fill out our values here, and basically we do that 12 times, and we get our box of convolution, or box of filters here, or feature maps, I should say. This is our box of feature maps. This is our convolution kernel matrix. And in case you're wondering, because it just slipped my mind when I was explaining this to you, because I did this slide a couple weeks before explaining it in this video. Now, you notice that before, we had a filter that was size 3 by 3, and we produced a smaller convolution or smaller feature map here. However, in this example, I'm producing basically the same size feature map. And this is actually what we need to do in most cases. We don't have to, but I'll explain to you how we actually end up with the same size image later on. But for now, just assume we run this. Let's say this is a 3x3 or 5x5 convolution here. We get the output here, and we fill in our feature matrix here, or feature map. So as you can see, this is how our filters look stacked up. You can visually see it quite clear there. So the outputs of our convolutions. From the last slide, we saw that applying 12 filters of size 3x3x3 to an input image, which was of 28x28x3, we produced 12 feature maps, so also called activation maps. Now these outputs are stacked together and treated as one big 3D matrix of output size 28x28x12. And this is now important. Go back to this here. This now forms the input, this big matrix here, to our next layer in the CNN. So now let's talk more about what these feature maps or activation maps actually are and how they represent image features. So now each cell meaning each 1x1 point in our activation map matrix is considered basically a feature extractor or a single neuron. And that single neuron is basically looking at a specific region as it slides over the image, or a specific feature, I should say, as it slides over the image. So if we have basically a feature map of say 28x28 like we just did, that feature map basically has each neuron, each cell basically activates depending on what it sees in the image. And in the beginning of our neural network, that of our CNN I should say, our convolutional layers basically are low-level feature detectors. And low-level feature detectors are basically looking for simple things in images. Simple things meaning like maybe edges, maybe specific colors, maybe a blob here and there. However, if we have consecutive concatenated convolutional layers, as in deeper networks with rows of convolutional layers, we can start detecting more spatial features like the face of a cat, or the shape of a bicycle, or the shape of a face. So that's how CNNs actually use these convolutional feature maps to detect features. So you've seen so far that we just use a standard arbitrary filter size of 3x3, but can we use other sizes, and how do they affect the convolution size and the future parts of the further parts of the convolutional neural net? So basically that's called tweaking the hyperparameters. So in the next section, that's section 7.3, we look at depth, stride, and padding. Hi, so welcome back to our chapter on depth, stride, and padding. These, I said, were the hyperparameters we use to actually tweak the size of the convolutional filter. So let's take a look and see. So remember, in our previous section, we only used a 3x3 filter or kernel, and that gave us this feature map that was actually smaller than the actual input layer. Now, does it always have to be 3x3? No, clearly not. It doesn't. And that's how we design our feature maps. We tweak some parameters, and these parameters actually allow us to control the size of the feature maps that we produce. So how do we do this? Well, clearly we can easily just adjust the kernel size. So instead of 3x3, we can do 5x5, 7x7. We can change the depth of those filters, and I'll explain to you what depth is just now. We can change the stride and padding. So let's talk about depth first of all. Now depth is not referring to the color depth here where it's 3 RGB colors. Depth refers to the number of filters we use. So remember in this example here, we have one convolutional filter that's being slid across this image, and that produces this one convolutional filter map. Well, we can have as much of these maps as we want. In this example, we use 12, but in reality, we can use 32, 64, any number of filters. And each filter, during training, actually learns different attributes, different features here that they end up corresponding to different features on this image. And I will explain to you, because right now that sounds a bit vague, like how do these filters actually end up learning different things? It has a lot to do with the random weight initialization and what it picks up during training. It's a bit of a black magic type thing, honestly, However, it actually does make sense when you actually drill down into it. So depth refers to the number of filters being used here. What about stride? Stride is quite simple to understand. Stride is basically the step size we take when we slide these filters across the input image. So let's take a look at what stride actually is. So remember, using a stride of 1, we just take a jump of 1 here, and then here again. So as you can see, this convolutional filter, or kernel, is just being passed one at a time, one cell at a time, and then when it goes to the bottom, it just goes here. So as you can see, this will produce 9 values in our output, and that output is called the feature map. Remember that. What if we use a stride of 2? What's going to happen to our feature map? Let's take a look and see. Stride of 2 takes a big jump here, so we only get 2 values from the top row, when before we had 3. Suddenly it's a big jump down here, so we only get 1 here, and then there's going to be 1 more here. So that means using a bigger stride of 2, we only get 4 or 2 by 2 feature map out of it. Now, is that important? And yes, it is, because think about it now. If you're using very big strides, you're going to end up with very small feature maps. And you don't always want very small feature maps, because then you lose information that's being passed from layer to layer. So this is how we now get into zero padding. Now, zero padding is actually a very simple concept. It refers to a border that we apply to the input volume. And why is this volume needed? Well, as you can see in our first example here, when we use a 3 by 3 filter and a stride of 1, we ended up with a 3 by 3 feature map. However, that is still smaller. And imagine we have a very deep network. Well, we haven't discussed very deep networks yet, but imagine we have a next series of convolutional layers after this. Like we use this as the input image now into a next convolutional layer. Right? So what happens in reality is that we have this going to this with a kernel here, then it happens again. Now, as you can see, it's going to get smaller and smaller, and we don't want that. We end up losing too much information, and it ends up being tiny at the end. So this is what zero padding actually does to the input image. It adds a layer of zeros right around it, and what that does is that allows us to actually generate a feature map that is the same size as the input image. So now, if you remember correctly, let's go back to one of my slides. Sorry about all these slides. In this slide here, remember, we passed this kernel across this image, and we ended up with a filter, a feature map, that was exactly the same size as the input image. And I mentioned before that in the previous section that intuitively you know that wasn't supposed to happen, but it did, and I didn't explain how. Now I'm explaining how. It's because zero padding was applied in this example here. So let's move forward to the other slides. Right, so looking at our zero padding example again, we can see how by moving this across, we end up with nice big feature map from the input image. So now we know that we have all of these parameters here. We have the kernel size, the depth, the stride, the padding, and the input image size. And we define these as K, D, S, and P, and I here. Now, this isn't actually calculating our convolutional output per se. Alright, that's actually fairly easy to do if you think about it. We know exactly what the size is, how much zero padding you would need to maintain that image size. However, if you want to make sure those settings that you use here make sense, there's a simple formula here, and it says I minus K plus 2P here over S plus 1. And basically we can use the values in a previous section where we used a 5 by 5 image. So it's going to be 5 minus 3, 3 being filter size K, plus 2 times 1, 2 being P, which is our padding, as I just said, plus 1. So that gives us a simple thing here, which is 2 plus 2 over 1 plus 1, which is 5. And as long as this formula gives you an integer value, basically you're okay. So let's move on now to ReLU, which is the activation layer of choice for CNN. Okay, so welcome back to our section on ReLU, which is the activation layer of choice for CNNs. So you remember when we talked about activation layers in our neural network section. The purpose of them was to introduce non-linearity to our model. And the convolutional process so far, as you've seen, is completely linear. So we definitely need an activation function to basically add some non-linearity. Why is that word so hard to say sometimes? To our convolutional neural network. So let's take a look at what ReLU actually does. So you remember this graph from ReLU? Basically it's a max function, a max zero function. What that means here is that any negative value that is outputted from a node in our convolutional neural net